Hello everyone, thanks for coming. I'm Zhang Fei from Linaro High Silicon Learning Team. Today I will report the accelerator framework UADK. The UADK is co-worked by Linaro and High Silicon for many years. It's an accelerator framework. So this is the agenda. We just give some status update. The VSVA and the UADK library update, and mostly our plan for the next half year. UADK is a general user space acceleration framework. It uses the SVA feature, so the user driver can directly use the virtual address for the DMA. It can for the better performance, and the SMU can do the page fault. So it will be very easy for user space accelerator. The SVA feature is already supported in the mainline kernel for several years ago, but the VSVA is using the UADK in the guest is more difficult. Currently still need one patch set. It already merged in the 6.16, just 2 months later, just one patch set. But the Cumul still need a lot of patch. We just do our private branch, so still a lot of patch outside. The last one is the most difficult, is line migration with VRMMU. It's still not supported. There is no mature solution now. So that's the most part, because the line migration is must required in the product, especially in the cloud space. The first is the VSV. VSV kernel, we always have a working branch checked by the every kernel. For example, the 6.5 and next is the 6.16. We always give our kernel branch, and also the Cumul branch. We also check the each working branch. So if you want to try, you can just use Linaro the working branch. There is a lot of patch already merged. Mostly like the deliver IO patch fault to the user space. Then in the guest we can get the patch fault. Also the nested translation and some VRMMU infrastructure. And the pass ID support in the guest. So this is already merged. And the last one is merged in the kernel next. Should be the 6.16, 2 months later. That one is used for the SVA feature, SVA fit and ROPF fit. Without that patch, we just have to do some hack, because it only enabled ROPF but not the SVA. So in the 6.16, the UADK the kernel is ready. The kernel is ready for the VSV feature. But the Cumul is still a lot of patch outside, so we can use our private git tree. Cumul just merged the basic RMFD backend, just very little. Still a lot of outside, like the VRMMU based infrastructure and the nested mode and our page fault. Then currently our working branch is a bit old, is Cumul 8, and we will rebase to the latest one, Cumul 10. Still a lot of patch outside. This is UADK library. UADK library currently it supports two features. One is the hardware accelerator, like the synchronous node is AES, DES, and SM4. Also the asynchronous like like Cipher Digest and many others. And we find in some scenario the CPU instruction has very good performance. So we also enable the CPU instruction like CE and SVE. It's very useful in a small package, has a very good performance. Currently, the UADK is used in many ecosystems like OpenSSL and Surf and DPDK, SPDK in many ecosystems, also in the big data. The problem is the problem is hardware and software cannot work together. You either choose hardware or you choose the software. So that's a counter problem. And our goal is to support the hardware and software together to aid scheduling for better performance. That's our current goal. This is the architecture for how to cooperate hardware and software. First we just use worker to abstract the hardware or software. It does not matter. The worker is accelerator, abstracted accelerator. It can be software, it can be hardware. It includes the resource. So in each algorithm, we just when the do operation, we just choose get worker. It will choose the best worker for the worker. The worker can be the software or the hardware. But the different algorithm can have the different policy. Because, for example, the ISA, the hardware is always better. For the cipher and digest, the small package, the software is better. So the mode is different. The compression and cipher and digest, they can be different mode, not the same. That's our new architecture. The first is the worker. Unlike before, we just use the worker to abstract the accelerator, including the resources. The worker will be the scheduling unit. It can choose when the working. We can choose. We can manually choose using hardware or software. Then we build a topology. Because when the system starts, the UADK library will pass all the driver in the system. And in the driver list, there are many, because there are CE, SVE, hardware, there are many accelerators. We just pass all the driver to the driver list. Then in the beginning, we will pass the driver list, choose the top 2 priority to the workers array. That workers array is using in the real scenario. And also user can do a manual configure. For example, there is a CE, SVE, and hardware. User can choose using a configure. You can choose CE or you can choose SVE and set the priority. The first one is the higher priority. The second one is the lower priority. And you can choose the mode. There are several modes now. The mode 2 is the threshold. The threshold for example, 1K. Below 1K, it will choose the software. The higher will choose the software. That's we can use a configure. That's a simple picture for one algorithm. The get worker will choose the real worker according to the mode, and the work array contains the accelerator according to the priority. And each session will choose its worker according to the mode, and there is no knock required because the station is working independently, so no knock. There's work. There's mode we will support. One is the primary. Primary means for example, normally we will do the hardware, but there is some error. We will switch to the software. That's the primary. The second is the round robin. Round robin is very simple. Just run hardware several times and then choose the software several times. Just round robin. And then threshold. Threshold is very important because in real product we get 2 difficulties. One is a small package. Small package hardware cannot get better performance, but because the package is like very small, the hardware need some time to switch, so it cannot get the better performance. So now we just you can see the picture. For small packet, the software is much better. For big packet, the hardware is much better. You can see the SM3 and SM4. That's reflected from the customer in the real product. And the second difficulty is the bandwidth. Currently, there is no method to decide to detect whether the bandwidth is full or not. Sometimes when the hardware gets the limit, the bandwidth is get limit, but the application there's no method to know whether the bandwidth is used of. So there's the hardware still not supported. We just use some other method. So it is in the to do. Well, you can see the algorithm is different. Like the SM3 and the SM4, the small package, the software is better. But for the ISA, the hardware is always better. So different algorithm is different. So they can use a different mode. For the ISA, we should not use the threshold. But for the Siphon Digest, we can choose the threshold. And also, we are not to pick one mode. It can, for example, in the digest, we can combine the threshold and the round robin. For the small packet, we just use the software. But for the big packet, we can use the round robin. So then you can decrease the bandwidth. So it does not matter using only one mode. It can use several modes together. So just like a mix. These are pictures performance of round robin. The threshold is very simple. Threshold just for the small packet it use software. So the performance software. The big packet is the hardware. So you always choose the better one. But for the round robin, is a different one. Round robin it doesn't have to be better than both software and hardware. You can choose. So there should be get the balance of loading the hardware and the performance. It does not have to be the best. We just do some in the Quantum 920. Do some. This is the round robin. So this our next plan in the next half year is add some more accelerator. Also since we have using worker to abstract the accelerator, our plan will also do the support the no SVA mode. But no SVA is not using the SVA feature, so it may use directly physical address. So we will, but currently use two API, different API. Our plan will combine using one API to support both SVA and no SVA in one API. So that's our next half year plan. That one, the VA firewall migration support. That's a difficult one. Currently, it's not supported yet, but it is must required in the product. We have a debugging branch. The difficult is currently we using nested translation. The guest has the stage one page table. The host the manager the stage 2 translation. The guest when the line migration happen, the guest directly copy the source guest to the guest and combined with page stage 1 page table. But the problem is whether and how to rebuild the stage 2 page table. The stage 1 page table is handles translation from the GVA to GPA, and the stage 2 is handles translation from the GPA to HPA. So when the source migrates to the guest, so the problem is the guest stage 2 translation have to whether or not have to rebuild. That's the problem. Well, currently we do some we do some patch to do the invalidation of the CD and the TLB. It works normally, but in some case it still get a fault. get stage 2 page translation fault. So it looks like we have to rebuild the stage 2. The difficulty for ARM is much harder. Intel case is much simpler because the Intel the QEMU contains the root pay table. It contains both the stage 1 and stage 2. So when the Intel case it move to the from source to dest, it can directly move all the pay table to the dest. So you just replay and get all the pay table. But on ARM is difficult. Is the guest contains the stage 1, but the stage 2 translation is on the host. So how to handle that host is still difficult. That's not supported yet. We'll do it later. Okay, thank you. Any questions? Thank you.